Good afternoon, ladies and gentlemen, and happy Easter. Whether you celebrate it or not, we're all off school at the moment for that reason. And of course, what that means is it is go time as far as revision's concerned, right? So whether you're in year 12 or whether you're in year 13, obviously you've got mocks coming up or actual full exams, okay? So that's why I'm here over Easter, to give you some tips and tricks and hacks and some advice really when it comes to doing A-level chemistry questions. Now, before we kick off, two things. Number one, who the hell am I? And number two, what are we doing today? Well, number one, if you haven't met me before, my name is Rich Warburton. I've been a chemistry tutor a science teacher stroke chemistry tutor for 20 years this year. I know, it looks like I've done 40, but it's 20 years I've been doing this for, working with all the different exam boards. So I got a real in-depth knowledge of all the different exams and all the specifications and exactly what you need to know. So as we go through here, let me know who you are, what exam board you're doing, if I've got any specific tips and tricks for these types of topics and question types and things as we go through. More than happy to help you. I want this to be really interactive, so please do say hi in the chat if you're here. And like I said, let me know your exam board, and hopefully we'll have some time at the end for some general Q&A. All right, you can pick my brains on stuff about how to revise for certain things, what types of questions come up, and so on and so forth. So in terms of again, who I am, I've set up chemistrycoach.co.uk. So that's basically where I just wanted to build somewhere where A-levels chemistry students could go to get reliable notes. Yes, there's all sorts of different places you can go and get free notes and stuff like that. But trust me, as I've been going, I've looked at those over the years, and I've kind of like, oh, okay, what are these guys all about? They're either not kept up to date or they aren't really exam board specific, okay? They tell you things that you don't need to know, maybe missing stuff out. What they don't do either is give you kind of examples of how, those sorts of things are examined. So that's what I wanted to do. I wanted to build somewhere where you can go and get the notes for free, and they are for free. You can go to chemistrycoach.co.uk and use the books, use the notes, okay? That's all my kind of knowledge and advice, and I've written that to kind of hopefully just make sense, all right? Notes that make sense. But obviously on top of that, there are other things that I've got there. So obviously tutorial videos, question packs, quizzes, the flashcards that I've made, no more kind of you go to these sites sometimes and there's oh, here's your A-level chemistry flashcards and there's 100 on VSCPR. Nobody's got time for that many flashcards. What I've done is I've made them really concise, really to the point, just the fundamental things that you need to remember. So they're not questions, they're actually just things you need to recall, like definitions and colors and reactions and so on and so forth. Anyway, enough about me. Enough about the site. Let's dig into what we're doing today. So we're looking at two things today. Number one is titrations. Okay, now titrations are, I don't know, once you've got your head around them, once you've kind of been doing them for a while, you kind of realize what's going on. But of course, the questions are all very different. All right. So I'm here to show you some of the classic things that you need to know and be able to do. And of course, how to attack those titration questions. I'm not here to tell you about what a titration is or, how to calculate concentration and moles and volume. You know how to do that, okay? What I'm here to do is to hopefully give you the confidence when it comes to these questions and give you some reliable methods that helps you minimize those mistakes, because we've all been there. We've all been there, and it's kind of yeah, I think I smashed that question. And then you look at it and it's oh, damn it, I forgot that there was a dilution involved, or I got my stoichiometry wrong, or I just didn't get my head around that practical at all. So, I'm here to kind of but essentially sort out the kind of wheat from the chaff and help you kind of just dial in on and help you understand what questions in front of you, and then you can apply your skills and knowledge and stuff like that. So that's titration tactics, okay? And then secondly, we're going to be looking at bonding, classic bonding questions, how to answer bonding questions, where students lose marks, and how to not lose those marks in bonding questions, okay? So like I said, this is a really interactive session. I want you to, just get in touch via the chat. If you got any questions at the end, then I've got time for open questions. So I'm going to do about an hour today. So it's really short, sharp, to the point. I know an hour sounds like a long time, but we know there's a lot to cover. There's a lot to talk about. Okay. Hey, Hafiza, how are we doing? Good to see you here. Thank you for coming along. So let's just get straight into it, shall we? So titrations. All right. couple of things first and foremost, okay? Yes, you think mole calcs. Everyone thinks mole calcs when it comes to titrations, and you're not wrong, but let's not forget there are all sorts of kind of practical based questions that kind of go around it, all right? So I'm here to kind of look at you know, the tactics and the kind of methods we can use to make sure we get all of those questions answered, okay? So all of those questions right. So let's just have a quick look at, you know, what I think is what the major things are that come up. All right. So what I'm going to do is just going to share my iPad here. So I've disappeared into the top corner. Hello. So this is an example of a practical chemistry book that chemistry coach members can get hold of. Okay, it's for WJC, AQA, and OCR. This is just the WJ one that I'm using. Okay, the things that we're looking at today are for all exam boards unless I explicitly state otherwise. So everything I'm about to tell you is completely relevant for your exam board, even if you're international or you're EdXL or you're in Scotland. Okay, so all of these things absolutely apply. So in here, first and foremost, you know, let's not forget about our practical errors. Okay, there's a page in here talking about the different types of error and how to calculate them. Now, of course, these are something that students worry about, but they come up, I don't know, irregularly. Okay, they're not in every year, but when they do, obviously you need to be able to do that. So read the question very, very carefully, and then you're able to calculate that percentage error. Okay, we should know that you know, when using a burette, we need to double this tolerance value at the top. Okay, so we need to double that, and the reason being is because we use that scale twice for one measurement. It's the same when we're using balances as well. Okay, so if you use a balance twice to get one measurement, so measuring mass by difference, then of course we need to multiply that tolerance value by 2. So ask yourself, when you're calculating these, have I used that scale twice to get one value? And the classic examples of those are burette readings, mass readings sometimes, and delta T, so difference in temperature. So if you get a calorimetry question and they ask you to calculate the percentage error or the percentage uncertainty in the temperature readings, make sure you double it at the top because you read the thermometer twice to get the delta T, the difference in temperature. So that's just a quick foray into that. I'll be talking more about errors. The more common questions that come up in terms of errors are the ones where they ask you, okay, well, the student's acid concentration was too high. What effect will that have on the mean titer or the titration volumes? Okay, so what I call consequential errors. Okay, so a student makes this mistake. How does that affect the final result? Or you know, there was water in the mass of solid that was dissolved. How does that affect the final result? And those sorts of things. Okay, so onwards and upwards. So firstly, okay, let's have a look at the precursor to doing titrations, and that's making up a volumetric solution. Now, this is really, really common. Like, it's a really, really common for all exam boards 6-mark question. Now, what you're expected to do is describe how you make up a volumetric solution. Now, these things I've written on here, okay, these are the points that they expect you to write for those 6 marks. Okay, so know your method for making up a volumetric solution. Classically, there will be a calculation at the front, okay, at the top of it. So they'll give you some instruction, like a student wants to make up 250 centimeter cubed of a 0.01 molar NaOH, okay? So that's what we need to do, okay? The first couple of marks in there are going to be for the calculations. Basically, what mass of solid sodium hydroxide do you need in the first place? So you use concentration and volume that you want to find the number of moles and then convert that into a mass, and then you can weigh that out using the method described below, and obviously using that difference in mass method to be sure that you get made the exact concentration. But then when it comes to the actual dissolving, okay, now these steps are super important. These are all things that gain you marks, all right? So anything in bold here especially, that's what they're going to be looking for in the mark scheme. So dissolving in a minimum volume of distilled water. Transfer the solution to a volumetric flask using a funnel. You rinse that beaker with distilled H2O and then add that to the flask, and that minimizes losses, okay? Making up to the mark and inverting to make homogeneous. So These things here, okay, are the things that are going to be put in a mark scheme. And it's a really common question. Just make sure you know it. But I'm going to make a general point here now. And that general point, I'm going to put myself on camera. That general point that I'm going to make about methods. Yes, it's important to know your methods for your practicals, all right? But know the reasons why you do some of these steps, all right? So yes, they might ask you to, they might give you a method and you have to look for errors in it. They might ask you to write the method for making up a volumetric solution. But the thing is, the most common type of question you get about practicals is why, okay? Why do we rinse that beaker and then add that to the volumetric flask? Well, it's to minimize losses. Why do we invert the volumetric flask at the end? Well, that's to make sure the solution is homogeneous, okay? Hey, Drew, will I be going over back titration questions? Oh, I have got you covered with back titrations, my friend, okay? I'm going to talk about question types in a second. So any method, and it's not just titrations, any method, okay? Ask yourself, why do we do that step? Why do we do this? So for example, in A-level, okay, if there's any A-level students watching, when we're recrystallizing, okay, to make an organic, a pure, dry organic product, why do we then dissolve our crude product in the minimum volume of solvent, okay, for recrystallization? The reason being is because obviously the smaller the volume, the more concentrated the solution, the more efficient the recrystallization is. Because if it's really dilute, you know, they've got loads and loads of solvent in there, it's going to be hard to bring it back out of solvent. So using a small volume there. So really important, write this down, know your method, but know the reasons why you do some of those steps as well. Ask yourself, why do we do that? So there's very specific details in those methods. Make sure you know why. Why? All right. So back to titration. So that's how you make up your standard solution. Really, really important. Now, different titration types. Now, these aren't for everybody. These are specific to WJEC, but the top two for everybody. Okay, Drew, if you asked for it, you kind of like kind of preempted what I was going to do here. So first of all, we've got what I call just a standard titration. Okay, it's basically where we've got two substances. Obviously, one's in our conical flask, one's in our burette. But of course, what we need to do is find the number of moles present in our unknown solution. Okay, it could be that we're asked to find the concentration of that solution. Let me just put a nice color on. It could be to find the mass of acid or base in the other solution, but it could be that we're asked to find the MR. Okay, but either way, it's just a standard titration. And it's all simple mole calcs to do that. Okay, so these are what I call like direct or standard titrations, but it's just what they ask you to calculate at the end may be different. Okay, it'd be nice to get one in the exam. Just find the concentration of sodium hydroxide. They're not likely to do that. They're more likely to go, okay, what mass of sodium hydroxide was dissolved to make that 250 centimeter cubed of solution? Or it could be, this hydrated salt was dissolved in 250 centimeter cubed of water. You know the mass of it. You then find the number of moles present, and you can use the mass and the moles to find the MR. So I'll talk to you about calculations later on, but the most important thing here is identifying what type of titration you've got. Most of the time, especially AS, it's going to be a standard titration. However, Drew, your back titration. Okay, so this is where an initial reaction is carried out between a substance, so a metal carbonate, or a metal oxide, and a known concentration and volume of acid. And the acid will always be in excess. Okay, so there's two reactions. Reaction number one is where you're reacting your unknown substance with an excess of acid, and it's always an excess of acid. We then make up to that to 250 centimeter cubed. And then that solution, the products, if you like, the solution of that reaction one is then titrated against a sodium hydroxide or something like that. Okay, so basically what you're doing is, imagine this. So this is all of the acid that you add into reaction one. Some of it was reacted, okay, in reaction one. What you're doing is finding out how much is left over. So if you know how much you started with in the first place, and you know how much is left over, you can calculate how much was used in that first reaction. And then using stoichiometry, you can find out, because you know how much acid was used in the first titration, you can then use it to find out the mass or the MR or whatever it is of that solid that reacted with that acid in the first place. Let me just show you something. So I've put together, there's a few bits about titrations here. Back titrations, okay? So this is a page in the book on back titrations where, you know, it's basically the simplest guide that I can give you, and using an example of how back titrations work. So once you get an idea of how back titrations work, you can identify them in an exam and go, okay, this is a back titration, all right? So this is what I need to do. This is what's going on, all right? And we'll talk about techniques in a second. Now, just for WJ peeps, really quickly, also what else is covered in here, my apologies for flicking around, is your double titration. This is it's quite a rare one, but it's one that you do need to know for WJEC. If you're AQA or OCR, then you don't need to know about these double titrations, okay? It's basically where you use two different indicators in one titration, so you get two tighter volumes in one, and it helps you find the kind of concentration or the volume of sodium carbonate. Okay, so I'm not going to spend too much time on that one, but back titrations and standard titrations are the order of the day. Okay, so let's have a look about how to attack a standard titration question, but I'll just show you just quickly what else is in here. So how to set up and the reasons why we do the things that we do in terms of prepping a titration, rinsing the burette, rinsing the pipette, so on and so forth, and how to deal with your actual values, your results that you get here. And everywhere, if you're a chemistry coach member, then obviously you can click on those QR codes, you can scan them with your phone, and that will take you directly to a video and a worksheet that I've put together to help you apply these skills and this knowledge that I've put in the books, okay? So we got standardizing an acid solution. I've put calculation pathways in here. Preparing a soluble salt by titration, more calculation pathways. So, you know, all the different types of titration that you need for your exam board, we've got in here, okay? So, you know, let's have a look and see if we can actually spot some different titration types, okay? So, titration questions. Let's have a look at one, shall we? So, this is, in fact, I will give you this right now, okay? So this, ladies and gentlemen, I'm going to put it in the chat. This is a link to this worksheet, okay? Sorry, words escaped me there. And here's the mark schemes, okay? So these worksheets, and you're welcome to them. I've basically grabbed all the titration questions I could find and put them in one place. And I've even put little notes on each one to say what type it is and like what you need to calculate at the end of it and so on and so forth. And if they include any error questions and this, that, and the other, because like I said, those are the ones that people forget about, okay? And it's all down to those consequential errors that you need to take into account. So there's the this pack that I'm using, okay? So let's have a look. Now, when it comes to looking at titrations questions, then what we need to do is obviously focus on, like, first of all, what type of question is it? The first piece of advice I want to give you is context, okay? Context. So getting an overview of what the heck is going on in this titration, okay? Now, this takes a bit of practice, and I'm still a fan of this now. And that's basically, if in doubt, draw it out. Okay, so let's have a look at this question. A student does an investigation to determine the MR of a solid of an unknown diprotic acid, H2A. Okay, so we want to find the MR of this. We're obviously reacting it with sodium hydroxide. So 250 centimeter cubed of an aqueous solution are used using 1,300 milligrams of H2A. So that's basically 1.3 grams. Okay. A pipette is used, of course, to add 25 centimeter cubed of 0.112 mole per decimeter cubed sodium hydroxide to a conical flask, and then we've got the results. Well, okay, so what the heck is going on? Firstly, let's have a look in terms of like where everything is. Now, most of the time, and this is coming from experience working with different students, is that a lot of errors occur where it's like, okay, I calculate the moles or something, but then you apply it to the conical flask or the burette, you get confused. Students get confused all the time about like, and lose their way with the calculation pathway. This is where, you know, the drawings and the mapping out, getting the overview, the context of the titration is really, really important. Get your head around it first before you start plowing in and do calculations. So this is what I do. Okay, so we got a conical flask. We've got our conical flask and burette. So in our burette, what we have is our H2A. Okay, now we know this is the mass of H2A that was used to make 250 centimeters cubed. So what we need to do is just make sure that we know that we got 250 centimeters cubed of H2A. That's going into our burette. And in our conical flask, we have got 25 centimeter cubed of 0.112 molar NaOH. All right. So in terms of our calculation pathway, okay, or sorry, in terms of our context, try this, okay? Use these questions to practice this, and you will get to the point where you don't really need to do it anymore. But my suggestion is, you know, just make notes somewhere, okay? Get the context of what the heck is going on in the titration. And before you even look at the question, what you can do is take a look and go, okay, well, if I can find the number of moles of NaOH in 25 centimeters cubed, then I can find by ratio, by using the equation, we can find the number of moles of H2A in the mean titer. Now, once we found the number of moles of H2A in the mean titer, we'll then need to find the number of moles, scale it up, okay, to find the number of moles of H2A in 250 centimeters cubed, and then we can use that and the mass to find the MR, okay? Because MR equals mass divided by number of moles, of course. All right, so that calculation pathway there is, well, it's basically 4 steps, essentially, okay, to get our 5 marks. So the drawing, like I said, helps you out figure how to get from stage 1 to stage 2 to stage 3 to get your answer, okay? So you're just literally following a pathway, and it minimizes the risk of you know, straying off the path, wandering off the path, and just, you know, it minimizes the risk of you making silly errors. All right, it minimizes the risk of you making silly errors. So yes, this is going to take up a little bit more of your time in a test or exam situation, but practice it now, okay? And then you'll get good at it, and it will save you time, okay? And it will reduce the chance of minimizing errors there, okay? So any questions on that, guys? Okay, in the chat, if you haven't got a question, just put no. That's absolutely fine. But if you have got a question about the kind of this sort of method, then just by all means ask me now. If you haven't, just put no questions. Nah, you're all right, Rich. Something like that. Just let me know you're there. You know, I'm just kind of talking to myself at the moment. Hafiza, could you add question pass slides to the workbook for each skill lesson? Yeah, that's something I'm working on. Thank you, Drew. Yeah, that's something I'm working on. So the question packs I've put together already in the course, they are kind of like a best of, if you like. It's not really every question, but you know, that's something I'd like to do eventually. But you know, stuff like this gives you lots and lots and lots and lots of practice. You know, that's what I'm giving it to you now. But you know, the key questions are the ones that I've put in the course, okay? Because sometimes it's not always about volume, but you know, it's more about knowing which type of questions that you're going to come across, okay? So, so draw it out, okay? Get your context, super, super, super important, okay? The other thing I'll mention while I'm here is always this, okay? All exam boards love to do this, and that's give you a number of titrations and then just go, okay, well, just make sure, you know, you use these titration values to get your answer. Well, obviously you need to select the correct ones. Know for your exam board what's acceptable in terms of concordancy. All right. Number 1, we never use the rough. Ever, ever, ever. Even if it's concordant with the other results, we never, ever use that. Okay. Now for OCR and for AQA, okay, they've got to be within 0.1 of each other. Okay. And for WJ, I believe it's 0.2. Okay, so they expect you to know what's acceptable in terms of concordancy here. Now, of course, looking at these results, we can obviously get rid of this one, and these two are our concordant results to get our mean titer. I should imagine that's where your fifth mark is going to come from, your 4 steps here, okay, or 3A, I suppose you can call this. But yeah, so just make sure that you're able to spot those titers. It's easy just in when you're kind of on a time limit doing these exam questions. And of course, it's going to be maybe something you slip up on, okay? But what we're always aiming to do when we're looking at these, especially big calculation questions and big practical questions, it's, well, all questions really, I suppose, but we need to think about being efficient, and we need to think about being accurate. All right. And that comes with practice. I'm a huge kind of exponent for practicing full exam papers in timed conditions. Okay. If you've seen any of my TikToks or anything like that, you'll know that. The reason is you've got to get match fit. You've got to get ready for those exams in the summer, the time pressures, the difficulty of questions. So by doing as many past papers, just for any subject, to be honest with you, doing as many past papers as you can under timed exam conditions. And one of the coaching sessions I'll be doing for Chemistry Coach members over the next few weeks is how to analyze. In fact, I think it's the first one, is how to actually analyze a paper when you've done it. Okay, so how to actually go, okay, well, what are my key learnings from this? What are my what do I actually do now I've got this result? Okay, and what are the most important things? So first thing with titration questions, context, absolutely important, so important. When it comes to back titrations, okay, I'll just show you real quick. So this is another question pack for you guys. And it is just back titration questions. Just back titration questions. So in fact, let me just find one in here, actually. Let me find I think it's the first one on here is a back titration. There we go. Okay. How do we recognize when we've got a back titration? Well, we're looking for 2 reactions, okay? So pure solid is thought to be calcium hydroxide. It can be identified from its MR. The relative formula mass can be determined experimentally. Here we go. By reacting a measured mass of the pure solid with an excess of hydrochloric acid. It's always an excess of acid, this first reaction. And in this case, it's just calcium hydroxide we're reacting it with. So we've got the reaction for the initial reaction. We got the equation, sorry. The unreacted acid, okay, can be determined by titration with standard sodium hydroxide solution. This is the number of moles and, this is the concentration and volume of HCl you're given at the start, okay? Outline giving brief practical details how you conduct an experiment to calculate accurately the relative formula mass of solid, okay? So it's not really a calculation question here. It's more of a method, like how do you use a back titration in order to find this, okay? So if I just go back real quick, we'll see our back titration here, okay? So this is how you do it, okay? Yes, we're using calcium carbonate here instead of calcium hydroxide, but the process is exactly the same, okay? So that question's a bit weird in that, just generally describe how you actually do this. But spotting that you've got one in the first place, there's always those things that jump out at you. Excess acid, and there's 2 reactions. 1, an initial reaction like we've just seen with calcium hydroxide, and then 2, a second reaction, which is your titration to find the number of moles of acid that did not react in the first reaction. In other words, what was in excess from that first reaction, okay? So you can use these books to help you kind of guide your way through these different titration calculations. But as I say, generally speaking, the best method is a logical approach, okay, when it comes to titration questions. By a logical approach, I mean that you need to understand the context of the question. Just take that extra 30 seconds rather than just diving in going, yeah, there's a practical here. Yeah, I got some titration results, mean titer, bang, and just go straight in. That's where mistakes can happen. That's where they trip you up, is by you missing out those little details in the practicals. Maybe they started with a concentrated solution of, acid. Then they diluted it, and then you use 25 of that. in your titration. And the question is, find the original concentration. So, don't forget, you'd diluted it first, then used it in the titration. So when working backwards, you find the concentration of the diluted one, and then that extra step to find the concentration of the original solution. Okay. Oh, hey, Ale. Nice of you to join us, mate. Thank you very much. The last thing I'll say about titrations, okay, is this. There's a 3-step method, okay? There's always a 3-step method. Yes, it is, sir. We're doing, we're just at the end of titrations, Ayub, and we're moving on to bonding next, actually. So, just caught the end of the practical side of things in titrations, okay? There's only 3 steps in any titration calculation, and they are always the same. Always the same. So if you're looking at a titration question, you're like, I have no idea what's going on here. There's always an in. There's always an in somewhere, okay? And what I mean by that is the first step in any titration calculation is always to find the number of moles of something, okay? So just look, okay? You know your triangles, number of moles equals conc times vol, number of moles equals mass over molar mass. It's always the first step in a titration question, okay? So the 3 steps are find the number of moles of something, okay, whether it's using conc times vol or mass over molar mass, all right? The second step always relates to the equation. So you're using stoichiometry. So don't forget, and it's a very simple thing, this, but don't forget it, is that if you know the number of moles of one thing in an equation, whether it's a reactant or a product, you know the number of moles present of everything else in that reaction, okay? So find the number of moles of something. It won't be your target substance, like find the MR of the acid, like in that question we looked at. But find the number of moles of something. Secondly, use stoichiometry, so use the equation to find the number of moles of something else. And then the third step, well, that can change, okay? It depends on the question itself. But I can guarantee you that 99.9% of all titration questions start with, okay, you got to find the number of moles of something somewhere and use stoichiometry in the equation for whether it's the titration or that initial reaction in a back titration, okay? So they're always the first 2 steps. Once you found the number of moles of your target substance, so let's say the H2A in that question we were just looking at, then where you go from there depends on the question. You might need to use a mass to find the MR. You might need to use a volume to find the concentration. So, that's where the context really comes in. But honestly, guys, do these titration calculations and you'll see the first 2 steps are always find the number of moles of something, then use an equation to find the number of moles of something else, okay? And then after that, you should be on the home straight. You should be able to see how you can get to that final answer, all right? So practice these questions and specifically take note of the questions they ask you about errors, okay? Because those are the most common ones that come up all the time. They will always ask you some sort of practical detail. So I'm looping back right now to where we started, and that's me saying, know your method, but know the reasons why, okay? And think about those consequential errors, okay? So for example, if you made up, let me just go back to the iPad just for a sec. If you made up a standard solution, let's not use red because that's angry. Let's say we made up a 250 centimeter cubed of solution, okay, and we overshot it, okay. So the student made up too much or added too much distilled H2O to the conical flask. Then we take 25 centimeter cubed of it and we put it in a conical flask, okay, and we're running our titration. Okay, so let's say this is NaOH, okay, and this is HCl. Now, if I overshoot this, okay, the concentration, and they're going to ask you, okay, so what's the effect on the tighter volume? Okay, what's the effect on the tighter volume if we add too much water to this volumetric flask? Well, what's that going to do? Adding too much water decreases the concentration of the sodium hydroxide that's in there. Okay, if you've overshot that that line at the top of the volumetric flask, that makes that less concentrated. Then when you put 25 centimeter cubed in here, the number of moles of NaOH is lower than expected. okay? What's that going to do to the titration volume? Well, that's also going to be lower than expected, okay? So that's an example of what I mean by a consequential error, all right? So they'll ask you, this happened, so what happens to this? So this is again where those little diagrams that I was drawing before about getting the context of the titration, that can really help you. So take it one step at a time, okay? And think, okay, too much water lowers the concentration. That means I got fewer moles in my 25 centimeter cubed in the conical flask, which means my titer volume is going to be lower. Just another one real quick. Let's say our sodium hydroxide was okay. Okay. Let's say our sodium hydroxide was okay. But when we first filled our burette with the HCl, okay, we rinsed it with water. Okay, with distilled water, we're supposed to do that. Okay, we always rinse our burette with water, but then we should always rinse with the solution as well. So rinse with HCl as well. Okay, now the reason we do that is to flush out any remaining droplets of water that might be in there. All right, but if we didn't do that, if a student rinsed with H2O and then just filled it with HCl, didn't rinse it with the HCl, but just rinsed it with water, what you're going to have are droplets of water in here. So the question is, if a student rinsed it with water, but then just filled it with HCl straight from there, how would that affect our mean titer, or how would that affect our titer volume? Well, if there are droplets of water in here, that's going to, when you fill it with HCl, that's going to decrease the concentration of HCl in there, only by a small amount, but it will decrease it. You might have 2 or 3 centimeter cubed of water still in there. Okay, so it could, lower that concentration of HCl by quite a bit. So if the concentration of HCl in the burette is lower, question, what's that going to do to our mean titer? Is it going to, what's that going to do to our titration volume? Is it going to increase our titration volume or decrease? Okay, remember we've got a set 25 centimeter cubed of NaOH down here. How is not rinsing it with HCl or not getting rid of the water from the burette, how is that going to affect the volume of your titer when you use it? Any answers in the chat, guys? No answers in the chat? Increase. Good. Thank you, Hafiza. So yes, a lower concentration means you need to add a greater volume in order to get the same number of moles into here to neutralize the NaOH, okay? So that's exactly what I'm talking about, consequential errors. Watch out for them and just take them logically one step at a time, okay? So again, that's where your diagrams come in. So in terms of titrations, folks, that's it. I mean, any questions on titrations here? Anything I haven't covered? Because we've got about 20 minutes, I'm going to be covering just some bonding stuff to kind of show you. And it's going to take a less time than the titration type of thing. But if you've got any questions about, whether it's the methods or whether it's the calculation methods or whether it's the errors, any questions whatsoever, then just let me know in the chat now. Otherwise, we'll move on to bonding. So whilst I'm just waiting for any questions to come through, I'll just say practice, practice, practice. And that's why I've put that worksheet together for you there, okay? So there's every type of question under the sun there, guys, from all the different exam boards. But you know what? A titration question is a titration question is a titration question. So you can't really go wrong by using other exam board questions as well, in the main for calculations, okay? Can we go through one calculation? Yeah, sure. I mean, let's do the one that we kind of started. So let's do this one. Yes, Ian, thank you very much. Better late than never there. All right, yeah, cool. How do you calculate percentage error work for back titrations? Okay, we'll come over that. We'll go over that a second, okay? Okay, so here, we've already mapped out our calculation pathway. Always think about the pathway for calculations. This is a really good, practice as well, actually. I'll just say, what I've done here, just rather than doing the calculations, maybe spend some time kind of going, okay, this is my logical set of steps for me to answer this question, okay? And just seeing that pathway, not necessarily even writing it down, just go, okay, if I find that, then I can find this, then I can find that, okay? So, thanks, I hope. There we go. Okay, so let's do this one. So where's my calculator? So first step, we find the number of moles of NaOH in 25 centimeters cubed. Notice how I'm writing exactly what I'm calculating, because just in case I need to go back and find something, I know what it is. So that equals conc times vol. So that is 0.112 times 25 over 1,000 as standard. So 0.112 times 0.025. And that gives us 2.8 times 10 to the minus 3. Okay, so that's a number of moles of NaOH in 25 centimeter cubed. Therefore, the number of moles of H2A in our mean titer. Now, what was our mean titer? I haven't calculated that yet. So that'll be 26.45, right? Don't need a calculator for that one. So that'll be in 26.45 centimeters cubed. So we've got our ratio here, okay? So it's a 2-to-1 ratio. So it's 2-to-1. So that equals, obviously, the number of moles of H2A is half the number of moles of sodium hydroxide. So we divide that by 2, and that gives us 1.4 times 10 to the minus 3 moles of H2A in 26.45 centimeters cubed. Okay, so that's where we found our mean titer there. But of course, we've got the mass of H2A in 250 centimeters cubed. Okay, so we need to scale up now from 26.45 centimeters cubed to 250. All right, so we do 250 over 26.45 times by our number of moles. Okay, and that will give us the number of moles in 250. All right, so we do 250 divided by 26.45 times 1.4 times 10 to the minus 3, and that gives us 0.0132 to 3 significant figures moles. Okay, now lastly, okay, our final step, notice how find the number of moles of something, use some stoichiometry, and now we're on the home stretch. So we need to find the MR, and that equals mass over molar mass. So the mass, not molar mass, number of moles, my apologies, habit. So that is 1.3 grams, 1,300 milligrams, divided by 0.0132. That is 98.2. Why not? 98.2 is the MR of our H2A. So you'll see step 1, find the number of moles. Step 2, use stoichiometry. And then step 3 varies on the question, but you can always get at least 2 marks into the question just by kind of doing those first 2 things. Okay. So IUP, how would calculating percentage error work for back titrations? It really depends on what they ask you. Okay. The percentage error in things is always calculated in the same way. Where am I looking now? Here. Okay, so percentage error is always this. Okay, now what they'll ask you to do, as far as titrations are concerned, they'll only ask you to find a percentage error in the titer, I should imagine. Sorry if you can hear the some yapping in the background. That's my dog Dexter having a good old snooze. He's probably chasing squirrels or something. So there's no difference here, IUP, in terms of your question, buddy. So in terms of the percentage error, that's okay, Hafiza, no problem. In terms of percentage error, you know, if they ask you about it for a pipette, okay, I'm sorry for the rubbish drawing of a pipette, you just use this. Okay, if you're using it for your volumetric flask, what's the error in there? Okay, you just use this. However, with your burette, because you read it once and then twice, okay, it's 2 times your tolerance value at the top divided by your reading. okay? So it doesn't make a difference, okay? It'll always just be about the titer. Those are the only ones I've ever seen, either that or your pipette or your volumetric flask, but they will give you the percentage error readings or the tolerance value readings, sorry, for those different bits of equipment. You just have to use it in the right way. Now, actually, last thing, and I thought, oh, it'll be half an hour on titrations. Here we go. Since we're talking about this, how do we lower the percentage error of our readings? Okay, well, we can't change the tolerance value of our burette or pipette or volumetric flask. That's fixed, okay? But what we can do is increase somehow the reading, okay? So let's say our titration, the percentage error in our titration was really quite high because maybe our mean titer was maybe like 8 to 10 centimeters cubed or something like that. That's quite a small titer value. If they ask us, oh, how can we reduce the percentage error? Well, we need to make sure that this number's bigger, okay? But we can't just say, use a larger titration. We need to think of a way of increasing that titer volume, okay? So we could use a less concentrated solution in our burette. If we use a less concentrated solution in our burette, ergo our titration values will increase in size because that would increase our titration volume, okay? So you can't just say use a larger titer volume. That's our dependent variable. That's the result of our practical, okay? Is the reading from the burette. So you can't just say, oh, get a bigger reading. You need to say how you're going to achieve a larger reading. So that's decrease the concentration of what's in the burette or increase the concentration of what's in your conical flask. Both of those will increase the reading, therefore reduce the percentage error, okay? Not more precise equipment, Hafiza. Don't fall into that trap, okay? That doesn't reduce the percentage error, okay? I suppose if you decrease your tolerance value, the more accurate it is. So yeah, your tolerance value gets smaller if you use more equipment. Therefore, yeah, I suppose that would decrease the percentage error. Yeah, there you go. So that would do it. There you go. Right, so we do need to move on to bonding, guys, because I'm going to run out of time because I am tutoring this afternoon. So, bonding. Let's talk about bonding, okay? So, couple of things here, all right? Just let me just stop sharing this for a second. I just want to show you something. This one. Okay, so three things I've got to share with you in terms of bonding, all right? I have got a bonding question pack that you can use to apply this to. So, okay. So this is what I want you to remember, okay? 3 points, okay? Write these down. Point number 1, make sure you can identify these bonding types. And this is for all exam boards, all right? So when you get bonding questions, and I'll show you a couple of examples in a second, the first skill you need to have is to identify, because they're going to be talking about different substances. Classic bonding questions, shapes of molecules aside. I'm not talking about shapes now, okay? But being able to look at a substance and go, that's the bonding in this substance, or these are the intermolecular forces in that substance. That is the first step you need to make, okay? So practicing that, knowing that, everything in the periodic table, obviously it's either metal, okay, so metallic bonding. It's either giant covalent, there's only 1 or 2 examples of those, or they are simple, okay, molecular or simple atomic, all right? You're not going to get anything ionic in your periodic table, of course, because by definition, that's a metal and a non-metal in old money. So looking at a substance and deciding, okay, what type of bonding is present. The second thing is being able to describe that bonding. So identify, describe the bonding. So you need to be able to describe, the bonding in ionic substances. Okay, there's your description there. Giant regular lattice of alternating cations and ions held together by electrostatic attractions. Obviously, covalent bonding as well. Okay, definition of that. And metallic bonding, okay, in one sentence, a regular lattice of cations surrounded by a sea of delocalized electrons. So in any bonding question that's usually linked to physical properties, the first two things you should always do: identify the type of bonding in each substance, describe the bonding in each substance, and only then can you explain the differences in physical properties. Okay. What I've also got in here, if I can just find it, is a list, okay, of all the different bonding types and physical properties that you need to know about. So these are our, obviously, intermolecular forces here, specific ones to AQA. This is the AQA book I'm looking at. And then, of course, you've got your ionic, metallic, diamond, and graphite, your giant covalent substances at the bottom, and their general physical properties, okay? But what I want you to remember is, okay, and I was thinking of something maybe more catchy, but identify the bonding, describe the bonding, then you can explain. So often students, when it comes to bonding questions, and it's the questions I've marked, students I've met in class and in tuition, when they lose marks on bonding questions and physical properties, it's because they don't identify the simple things to start with. Okay, for example, in fact, I will just share this with you. It's not a massive one, this one, but it's it's important. So there's some bonding questions, and this is the sheet. Okay, so for example, 6 marks. All right. This question is about sodium and some of its compounds. Fair enough. Use your knowledge of structure and bonding to explain why sodium bromide has a melting point that is higher than sodium and higher than that of sodium iodide. So for these 6 marks, okay, some people just jump straight into this. Okay, identify, describe, explain. Set your stall out first. This is where 90% of students are losing marks on bonding questions, I promise you, okay? So you've got NABR and NAI are ionic, of course, okay? So again, that skill in identifying what the bonding in a substance is. You can say that they have strong, can't write today, strong electrostatic attractions between the alternating ions, okay? Then you can say that Na is metallic. Okay, so we've identified, let's describe, and we just say a regular lattice of positive ions, and I'm using shorthand here, surrounded by sea of delocalized electrons. Okay, now there are electrostatic attractions between the electrons and the positive ions. Okay, so all I'm doing here is setting out my stall. That's at least 2 or 3 of the marks of these 6 just by making those statements. We haven't even got to the explanation yet. Okay, so that's really, really important that you're able to do this. And these are the marks that students miss. Now, what any question boils down to when it comes to physical properties, and especially melting and boiling points. Let's use melting and boiling points because this is what the question is about. It's about a melting point. They are giving you the answer. Okay, so what you need to say is that sodium bromide, okay, has a higher melting point than Na, as the electrostatic attractions between Na plus and Br minus are stronger than between the positive ions and delocalized electrons in sodium. Okay, we are comparing two very different substances here, an ionic substance and a metallic substance, but it's all about electrostatic attractions. Any type of bonding is about electrostatic attractions, even covalent. Okay, so all we need to say is, well, you know, these electrostatic attractions, because it's got a higher boiling point, NABR, melting point, sorry, the electrostatic attraction between this and this in NABR must be stronger than between the delocalized electrons and positive ions in metallic bonding. So therefore, and this is the kicker, more energy required. Okay, that's what they link to, because of course it's got a higher melting point, because more energy is required to break those electrostatic attractions and melt it. Okay, now we've already set our stall out and we've said that NABR and NAI are both ionic bonding. Okay, so what we can say now is that let's play spot the difference. Na plus and Br minus, and Na plus and I minus. Now this has a higher melting point than sodium iodide. Okay, let's play spot the difference. Why do you think? Because these electrostatic attractions here in NABR must be stronger than the electrostatic attractions in Na plus and I minus. So why is that? Why is that? Any ideas in the chat, please, guys? Good. IOB. Love it. Okay. Br minus has a greater charge density. So increased charge density in Br minus. Or we could say that the ionic radius of Br minus is smaller than that of I minus. If you think about it, we've got our sodium ion, okay, and here's our Br minus ion here, okay. If we take our sodium ion and our I minus ion, okay, if I put that in the middle, we've got an extra layer of shielding here, okay. So that just increases the distance between them, okay. So that's what IOB means by charge density. They're both 1 minus, okay, but because this is smaller, it's more dense, okay. So that means there's going to be a greater attraction between the positive ion and the negative ion here, okay. So what you can see in terms of constructing our answer here, in terms of the differences in properties of things, okay, is identify the bonding in each substance, describe the bonding in each substance, and then you've done most of the legwork, and all you need to do is just spot the difference between them, okay, or explain the difference between them in terms of that physical property. So let's do one more example real quick. Okay, here we go. Methoxymethane, okay, is an isomer of ethanol. Okay, so they both have the same MR if they're both isomers. Okay, so that's one little insight we can make there. We've got the boiling points of them. In terms of the intermolecular forces involved, explain the difference in boiling points. Well, they're both got the same MR. Okay, so therefore the same induced strength of induced dipole forces. Okay, because remember, every single molecule, every single substance, every single molecule, let's say, has induced dipole forces. It's just that we always tend to reference the stronger one if it has a stronger one. Okay, but let's not forget that plays a part as well. It's the reason why, propanol has got a higher melting point than methanol. They're both hydrogen bonding, but the propanol has got a greater MR, more electrons involved in the induced dipole, so therefore that's going to have the higher melting and boiling point. So let's not forget, ID forces are in everything. Now it's a game of spot the difference, okay? Ethanol's higher, that's because that's got hydrogen bonding in it, because we've got hydrogen directly bonded to an oxygen. Whereas in methoxymethane, okay, our CH3, then an O, then a CH3, there's no hydrogen bonding here because we don't have hydrogen directly bonded to an oxygen, okay? But what we're looking at here is basically induced dipole forces. So that's why that's low. Hydrogen bonding is stronger than induced dipole forces, so that's why they require more energy to break. Okay, so again, set your stall out, identify the bonding or intermolecular forces in each, describe them, and then you can explain the difference between the two. Okay, and there's another one in here as well. Classic, okay, 3 substances, explain why the melting points of these substances are different for 6 marks. Identify ionic, simple molecular, or simple covalent, induced dipole only because it's non-polar, and simple molecular again, but this time permanent dipole because it's got 2 different elements bonded together. Okay, there's a difference in electronegativity there. The question is, why is chlorine, even though that's a non-polar diatomic molecule compared to a polar HCl, why do we think chlorine has a higher melting point than hydrogen chloride? Even though this is induced dipole, which is weaker than permanent dipole in the HCl. Answers in the chat. Why is it that Cl2, even though it's non-polar and induced dipole only, so the weakest form of intermolecular force, why is it still higher than HCl? Any takers? No? That's okay. Well, think about this. It's because its MR is greater, okay? It's got an MR of 71, this is only 36.5. So there's loads of electrons, okay, involved in this particular induced dipole in chlorine, okay? So it just so happens that these induced dipole forces, because there's so many electrons involved, give the Cl2 a much stronger intermolecular force, even compared to a permanent dipole in HCl, okay? So just last thing, going back to this, I just want to make this point. Back to the original page here. These induced dipole forces technically can be higher than hydrogen bonding if the molecule is large enough. Okay, let's say if you add, I don't know, C30H62, you know, like massive long chain hydrocarbon, that's going to have a higher melting and boiling point than, of course, ethanol, all right, which has got hydrogen bonding, but it's only a small molecule. So when you think of induced dipole forces, yes, they are the weakest of the intermolecular forces. But if you take the size of the molecule into account, the number of electrons, that's key. If you take the number of electrons into account, and it's just such a large molecule, these induced dipole forces can be really very strong, okay? So if you see a question like we've just seen where it'd be like, that doesn't make sense, Cl2 is induced dipole and HCl is permanent dipole, that goes against everything I've ever taught. Well, all you need to say is that because Cl2 contains many more electrons, the induced dipole forces in chlorine must be stronger than the permanent dipole forces in HCl. Okay, so let the question guide you. They are telling you which has the highest melting point and boiling point. So go with it. And all you need to say is, well, therefore, the attractions in this one must be greater or stronger than the attractions in the one that's got a lower melting and boiling point. That's all you have to say, okay? But identify the type of bonding or intermolecular force, describe the type of bonding or intermolecular force, and then you can explain the difference between them, okay? So remember, IDE, identify, describe, explain, and you'll get all the marks, okay? And use that to plan your answers out as well. So, my lovers, got all West Country on you there. Where are we? Let's go back here. So that's today, okay? So titrations, tick. Bonding questions, tick. Now, just as a reminder, from the 27th of April, for Chemistry Coach members, I'll be running basically exam coaching, all right the way through. I've basically lined up things like how to attack 6-mark questions, how to analyze your paper once you've done it in practice, okay? So doing past papers and timed exam conditions, what you do with those afterwards. You know, how to attack long calculations and things like that. So there's loads of techniques that are useful for everybody. It's not revision, okay? I'm coaching you through the revision process and coaching you through the exams, and there'll always be a bit of time for the members to ask me questions as well, okay? So, before I go, let's have a couple of minutes if we need it. Any kind of one-off questions that you guys have thought of that you might want to ask me? Jay, oh, this is the kind of this is going to haunt me for a while. Jay, yes. How similar is your course to the one on TT? Well, considering I wrote both of them, very similar. Okay, I mean, obviously, everything boils down to being exam board specific at the end of the day. So yes, I was part of TT for a few years. I did write and record the entire course there. I'm no longer affiliated with them in any way, but it's all the same material. What I've done is since then I've gone away and thought about how best to provide useful resources and information to students. And I think what I've got at Chemistry Coach is more efficient. It's in terms of time saving, because many of the videos that I made were kind of like, okay, here's a 8 to 10 minute video on just equations you need to know. Well, do you need to watch an 8 to 10 minute video on that, or do you just need it in text format where you can just download it? Okay. So the course that I've got now, okay, you got free access to all the notes. All you have to do is go to Chemistry Coach for WJC, AQA, and OCRA. You can go and use the notebook, okay? You can use the notes for free. It's all interactive. You can even search it 100%, okay? So everything in there is exam board specific in terms of the facts and the knowledge you need for your AS and A-level chemistry. But if you're a Chemistry Coach member, you've got question packs in there. You've got my skills videos, which show you how to use the information that you learn in the notes, and got question packs that I've written as well to kind of go through the different major question types to identify those. You've also got flashcards that I've written, which are really very specific. Okay, there's not too many of them. They focus on the major facts that you need to remember for your A-level chemistry. There's very few for amount of substance, because there's nothing to remember there. It's all skills based, which is why there's more videos in the amount of substance. Whereas something like Group 2, Group 7, there's very few videos there, but there's more flashcards and things, because that is more kind of like that recall side of things. Okay, so it's built and giving you the resource which is going to be most helpful for each of those individual topics. I've also got obviously the AI. Actually, let's talk about AI for a second. Anybody using AI to help them study? Give me a yay or an A. The big difference actually is that Taylor Tutors is £80 a month and mine is just £80. That's it for the entire year. Well, until the 1st of July anyway. Okay, good. Be careful, all right? If you're using ChatGPT, it goes off piste. It starts doing weird things. It starts filling in the blanks. AI is very clever, and because it's very clever, if it's not sure if you need to know something or it doesn't know something, it's going to go away and grab just anything it can find in the World Wide Web to kind of fill in those blanks. I have tried so many different ways to make it exam board specific. I tell it, use the AQA specification. I only need, tell me what I need to know about transition metals or which delta H's I need the definitions for. And it doesn't matter what you type in, it's going to give you stuff you don't need to know. Okay, which is why I have built this. Okay, so this, ladies and gentlemen, is a little insight into the Chemistry Coach AI. Okay, so what I've done is I've loaded it with all the resources from Chemistry Coach. So I've written all the resources here, and I've given it very, very specific instructions to be 100% specific to your exam board. So not giving you things that you don't need to know. Okay, it will only ever give you stuff that's in the specification. It will only ever reference and give you question types like you get from the exams, and it'll do anything you want it to do. Okay, so for example, if I just type in here, write me a multi-step, if I can spell it, multi-step exam style question on a back titration. Give me the answers at the end. Boom. Dodgy. I shouldn't do stuff like this live just in case it doesn't do what I want it to do. But Hopefully it will, and typically it's been very slow whilst I'm showing you. Usually it's pretty fast, but you can ask it to do anything, right? You multiple choice questions. You can even upload a question. Let's say you've written it on your iPad, and essentially it'll do that for you. Okay, so oh, it's gone all weird. Why has it gone all weird on me? Oh, this is classic, isn't it? That I've just kind of shown you this and it's gone all weird on me. Let's try this again. All right. I don't know why it's done that. Okay, so write me 10 multiple choice questions on identifying types of bonding. So, Hafizo, which part of the booklet links to water of crystallization? So, water of crystallization, let me just pause this for a sec. Water of crystallization, that is, well, it depends. There's titration one and there's a gravimetric analysis. Both of those are in the book, okay? So in the practical guide. That's why I've done that, okay? So I've put that in there, so because it's part of the spec and those are typical questions that you get. So you can find that in the practical booklet, Hafiza, okay? So I'm going to go away and find out why my AI is being all squiffy, and it's typical, isn't it? I've shown you this live and it's kind of just thrown a wobbler, but I'll check that out. But I can promise you that it does work. That's classic, that is, isn't it? Anyway, I'll probably do another live just showing you actually, so with it actually working. I don't know why it's done that. I think I know why. I know why. It's because it's been updated, because it's using Gemini. Okay, so Gemini's just updated to 2.5 and I've written it for Gemini 2.0. So I'm going to fix that, and I'm going to show you guys again tomorrow it actually in all its glory. Okay, so that's me for today. So tomorrow, let's just check out what we're doing tomorrow. Tomorrow is all about atomic structure and the importance of atomic structure. What it is, it's about linking topics. Okay, using your knowledge and applying it to help you figure out answers to other questions in other areas. So the importance of atomic structure and mechanisms. We're going to be looking at mechanisms as well tomorrow, how to understand mechanisms and how to actually kind of just not just recall mechanisms, but understand them and apply that knowledge in exam questions as well. So we'll talk about all the different things that we can do in terms of helping us for mechanism questions. Okay, so I love you and leave you, and I will see you tomorrow at 1 o'clock, guys. All right, you take it easy, and I'll see you soon.